Good morning, my dear students of class 11. Today we will be discussing about hybridization and its application. In our previous video, we had discussed about hybridization involving s and p orbitals. Today we will be discussing about hybridization where d orbital is also involved. So this is the application part. Here we will be having three types of hybridization involving d orbital. Here in class 11 we will be discussing this. Okay, so for example, let's discuss an example. In molecule like PCl5, we will be seeing what kind of hybridization is involved. So you know the atomic number of phosphorus, it is 50. Its electronic configuration 1s2, 2s2, 2p6, 3s2, 3p3. So this is the hybridization of this electronic configuration of phosphorus. So in the outermost cell you have this 3s and 3p orbitals. So while in our previous video also we had discussed about ground state and excited state of elements, phosphorus here is the central element in case of PCl5. So we will be taking only the outermost orbitals, that is s and p orbitals. Here the electronic configuration, in s orbital you have 2 electrons and in p orbital you have 3 electrons. They have to singly filled first. Okay, so whenever it gets excited, then what happens? Since phosphorus lies in third pair, it contains vacant d orbital. One, two, three, four, five. So whenever it is in excited state, one electron is paired in 3s orbital will be shifted to the d orbital. Therefore, you will be having how many unpaired electrons here now? 5 unpaired electrons. So these are the orbitals which contain these unpaired electrons are what? Hybrid orbitals now. And now this will be used in bond formation with what? Chlorine atom. How many chlorine atoms are there? 5. So 2, 3, 4 and 5. Since chlorine also needs 1 electron to be octet, therefore it goes and forms covalent bond with phosphorus atom. Now in this case we can see which orbitals are involved in this bond formation. This is 1s orbital. How many p orbitals? 3 p orbitals and 1 d orbital. Up to this point electron is present and it is used involved in bond formation. Therefore how many orbitals? How many orbitals of d is involved? Only 1. Therefore its hybridization is sp3 dehybridization, and the geometry of such molecule will be phosphorus will be the central element, and the 3 chlorine atoms will be lying at the corners of the equilateral triangle. This 3 will be on the plane, okay, on the plane, one above the plane, the other one below the plane. Now this will be above the plane and another chlorine will be forming the bond below the plane. These 3 are what? These 3 are lying on the sides of the equilateral triangle, and here you have this bond formation 1, 2, 3, 4 and 5. Okay, and the geometry, the structure. The geometry of this structure is known as what? Trigonal bipyramidal. Trigonal bipyramidal. That's bipyramidal. Okay? And these 3 bonds are known as equatorial bonds. It is equatorial, and these two bonds which are lying out of the plane and below the plane are known as what? Axial bonds. Okay, so this is what you have to know about hybridization, sp3d hybridization. Now then let's discuss about sp3d2 hybridization. You have to remember the geometry. Okay, if it is sp3d hybridized, then it is going to have trigonal bipolar geometry and its structure. Now let's discuss about sp3d2 hybridization. sp3d2. The second example. Here we have sulfur hexafluoride SF6. So sulfur atomic number is 16, electronic configuration 1s2, 2s2, 2p6, 3s2, 3p4. This is electronic configuration. Now these are the outermost orbitals. So sulfur in ground state. Sulfur in ground state will be having these 2 electrons and these 4 electrons. 1, 2, 3 and 4. Now as you know, sulfur also lies in which period? It lies in period, third period. Therefore we also have a vacant orbital. 1, 2, 3, 4, 5. So here, now once it is excited, what will happen? This pair of electrons will be shifted to the vacant d orbitals. This here it has d orbital and the electrons here are not present here. Therefore, electrons will be shifted to d orbital, 1 electron from here and 1 electron from here. So now in excited state, sulfur will have how many unpaired electrons? 6 unpaired electrons. Now fluorine needs 1 electron to complete its octet and become stable. Therefore, now it is involved in bond formation with these orbitals of sulfur. These are hybrid orbitals of sulfur. Now here you can see that 1s is involved. How many p are involved in bond formation? 3. And here how many d? 2. Therefore its hybridization is sp3d2 hybridization. So the structure of the molecule will be the 4 fluorine atoms lying at 4 corners, 1 above the plane, the other 1 below the plane. Okay, so these 4 fluorine atoms are lying on the plane. Okay, 1 above the plane, the other 1 below the plane. The geometry, the name of the such structure is known as octahedral structure. Octahedral structure or geometry. In such structure, in mathematics, whenever it comes to numbering, so octa means 8, but never be confused. Whenever we are doing about hybridization and whenever we are discussing about this geometry of molecules, octa means 6 bonds. Now let's discuss about one more type of hybridization where d orbitals are involved. That is sp3 d2 hybridization. sp3 d2 we have discussed. Now we will be discussing about sp3 d3 hybridization. So example of such molecule will be IF7. Okay, so iodine lies in group 70. Therefore, its electronic configuration will be NS2, NP5. Group 70 means in the outermost cell it will be having how many electrons? 7 electrons. Therefore, 2 plus 5 is 7. So if you don't want to write in the learned form, then you can write in this manner also for doing hybridization. So you know iodine, let me tell you once again, iodine lies in group 7. Therefore, it contains 7 electrons in the valence. So in s orbital, it will be containing 2 electrons, and in p orbital, it will be containing 5 electrons. So iodine in the ground state will be having 2 electrons in s orbital and 5 electrons in the p orbital. Now iodine, whenever it is excited, then since it contains d orbital, this pair of electrons will be shifted to d orbital. 1, 2, 3, 4, 5. So here 1, 2, 3, 4 electrons. This 3 will be shifted to the d orbital. 3 pairs of electrons in the ground state, whenever it goes to excited state, will be shifted to the d orbital. Now here chlorine needs 1 electron to complete its octet. Therefore, it comes and forms bond with these hybrid orbitals of iodine. Okay, so here you can see 1s, 3p, and 3d orbitals are involved. Therefore, its hybridization is sp3 d3 hybridization. The structure of such molecule will be pentagonal bipyramidal. That is iodine lying at the center, and you have pentagon. Okay, here at the sides, at the vertex of this pentagons, we will be having a chlorine molecule. These 5 fluorine atoms will be lying on the same plane. Please don't forget that. Then 1 will be lying above the plane, 1 will be lying below the plane. Okay? So this is the structure of I7 pentagonal bipyramidal. Pentagonal bipyramidal. Why pentagonal? Because this 5 fluorine atoms are lying on the same plane, like a pentagon at the side at the vertex of pentagon. And why bipyramidal? Now 2 fluorine atoms. 1 means mono, 2 means what? Bi. So 1 is lying on the plane, the other one is lying below the plane. So these are very important points. You need to practice this, okay? Hybridization, and you have to learn the structure and the geometry of these molecules. Now, here in this case, you saw that in the hybridized state, whenever it was forming bond, lone pair were present. Therefore, this geometry were true. Now, whenever you will be having lone pairs of electron, now that is going to affect the shape of the molecules. Now, before this, we are going to discuss about VSEPR theory. Valence shell electron pair repulsion. Okay, valence shell electron pair repulsion theory. So here they have given you certain postulates. You can refer to your book as well. Okay, so let me tell you what. There are 5 main points. So let me read it out. And after reading it out, application part we'll be discussing on the board. So the first point says us the unpaired electrons in the valence shell. Okay, the unpaired electron in the valence shell of central atom. Now, these are involved in bond formation with the unpaired electron of surrounding atom. That is the first point. So, therefore, the purpose of bond formation, there has to be what? Unpaired electron. This is what this first point tells us. Number 2, being similarly charged. You know, if you have similar charges, they always repel. The second point is that being similarly charged, the bond pairs as well as the lone pair tend to repel one another. That means whenever you have lone pair as well as this one pair, then since electrons are involved and there you have negative and negative charges, they are always going to repel each other. Number 3 point, electron pairs around the central atom can adjust themselves with respect to one another in such a way that the force of repulsion among them is minimal. So, if you have lone pair, two electrons, now they won't remain as far as possible, because if they come very close, they will repel each other and then it becomes very unstable. Therefore, now they tend to go far away from each other to be stable. Okay. The fourth point, the force of repulsion is minimum when the electron pair are far away from one another. The same point. Now, if you have electrons, negative charge very near to each other, they always repel. Therefore, they want to stay as far as possible. And the number 5 point is, in a compound you have lone pair as well. In some of the compounds you will be having lone pair, you will be having one pair. So there you will always be having what? Repulsion. And the order of repulsion. So this is the main point. The order of the repulsion will be, you have lone pair. This is lone pair repulsion. Okay, lone pair repulsion. That means if you have two lone pairs, lone pair, repulsion is greater than lone pair, bond pair repulsion. Okay, and this exists in bond pair repulsion. So I need to say this point tells us that suppose you have, say, water molecule. Let me give you an example. Water molecule. Water, as you know, it will be having two lone pairs. Now, the repulsion between this lone pair and this lone pair will be maximum. So they will repel each other to the maximum extent. Okay, this means lone pair. You can see lone pair repulsion is maximum. Now here they are telling us lone pair, bond pair. Now here you have lone pair, and this is lone pair, this is bond. That means this is lone pair, bond pair repulsion. This is lone pair repulsion. And here you can see that between these two, hydrogen and hydrogen, here you have hydrogen bond, here also hydrogen bond. So this is your bond pair. Okay, and the repulsion between them, this hydrogen and this hydrogen, is minimum. So I hope you understood this order of repulsion. Now let's take some examples. Okay. Now in your book, you have a table. And this table you have to remember it. Sets of molecules and the number of electrons pair around the central atom. So sets of molecules. Okay, so you have to remember this table. Number of electron pair around the central atom. Now, geometry of molecule. Geometry of molecule and examples. Bond angle is also there. Bond angle and examples. So okay, so this is your So now let's take examples. Now here, number of electron pairs are on the central atom. This electron pair doesn't mean it's lone pair. It means electron pair. Okay, bond. So in the formation of a single bond, two electrons are involved. This particular Okay, this topic, this particular instruction is that. So here, suppose you have two pairs, means two bonds, two pairs. Then it's whenever you have two pairs, and if lone pair is absent, then the structure of the molecule will be linear. Suppose if you have an example here. You have beryllium chloride. So this beryllium chloride will be having linear structure. Can you see this? Looks like a line. So this is the linear structure. Okay? And the bond angle here, you know, it is 180 degrees. Similarly, if you have three pairs, then its geometry will be trigonal planar. Its geometry will be trigonal planar. Trigonal planar. Trigonal planar means, let me give you an example. First, BF3. Example is BF3. So the structure of BF3 will be boron will be lying at the center, and the three fluorine atoms will be lying at the sides of the triangle, equilateral triangle. So here you will be having fluorine, here you will be having fluorine, and here you will be having fluorine, and the bond angle, you know, of the equilateral triangle. Here the bond angle here is what? The bond angle here is 120 degree. So if you have four pairs, then its structure will be tetrahedral. You know this tetrahedral. Example CH4, methyl molecule. Bond angle will be 109.5 degree, and its structure will be, you'll be having this structure: hydrogen, 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 and hydrogen. Okay, so this points you have to remember. And here you can see that there is no lone pair. If lone pair is absent, then you will be having this geometry. You have to remember this. Okay, and if you have five pairs, then we wrote this part, the structure. While doing your notebook, please draw the structure as well. If you have five pairs, then its structure, geometry will be triangle bipyramidal. Triangle, gonal, bipyramidal. Example, just we saw today's first. So if you have five pairs, then its geometry will be triangle bipyramidal. And its example today we saw the example of triangle bipyramidal. It is PCl5, and it was having sp3 dehybridization. And the structure or the geometry of PCl5 we have already discussed. Now, if you have six electron pairs around the central atom, then its geometry will be octahedral. And the example of such molecule is SF6, that also we saw today itself. So you have to remember. Now this geometry is true if you don't have lone pair of electron. Okay? So if you have lone pair, then they will be distorted because there will be changes in the shape of this molecule. So that part, let's discuss now. So I told you this geometry is true if that particular molecule doesn't have lone pair of electron. If lone pair is present, then it will deviate from its geometry. So let's take an example. Now, suppose you have, say, methane molecule, you have ammonia and water molecule. Now, if you do its hybridization, you will see that methane has sp3 hybridization. Methane has sp3 hybridization. Ammonia too has sp3, and water molecule as well has sp3 hybridization. So all of them are sp3 hybridized, but they still have effect. Now, according to hybridization, you saw from the table, you can see, refer to your book. If it is sp3 hybridized, it is supposed to have which geometry? It is supposed to have tetrahedral geometry. Tetrahedral geometry. Okay? In methane, there is no lone pair present. That means it doesn't have lone pair. In ammonia, you have a lone pair. Means one lone pair. And in water molecule, it has two lone pairs. Now, these lone pairs. Now, whenever you have lone pair, I told you, it will not be having the same geometry. It will disturb the geometry of the molecule. According to hybridization, it is sp3 hybridization, all of them. And if it is sp3 hybridization, then they are supposed to have what? Tetrahedral geometry. Now, this is true in case of methane molecule because it doesn't have lone pair. No lone pair, therefore now it is going to have what? Tetrahedral geometry. In case of ammonia, since it has a lone pair, then you know lone pair repulsion, lone pair and bond pair repulsion is more than that of what? Bond pair repulsion. Therefore, what will happen? Nitrogen. Here you will be having lone pair. Now this lone pair pushes these three hydrogens far away from each other. Therefore, now it is going to have what? Pyramidal. Its geometry is what? Pyramidal. Now in case of water molecule, since it has two lone pairs, now let me draw a structure then. Two lone pairs will try to remain as far away from each other as possible because its repulsion is maximum. Because of that, now this lone pair repulsion forces its bonds to come very close to each other. Therefore, now you can see, if you just look at hydrogen, oxygen, and this hydrogen itself is what? Viscid, or it's what? Bent. Now, let's discuss about bond angle. Tetrahedral geometry, what do you know the structure of tetrahedral? Carbon is present here, hydrogen, and hydrogen. The bond angle here is 109.5 degree. Okay, in case of tetrahedral geometry. Now, if you have a lone pair, then its geometry is what? Pyramidal, and the bond angle over here is what? 107 degree. So you can see that this lone pair is forcing these bonds to come little closer to each other. Now, whenever you move to this water molecule, then since it has two lone pairs, means more repulsion. Now, this bonds, hydrogen and hydrogens, now they will be forced to come even closer than in case of what? Ammonia. Here, the bond angle will be 104.5 degree. So you saw that because of the presence of what? Lone pair, these certain molecules, they have deviated from its expected geometry. It was expected to have what? Tetrahedral geometry because its hybridization says also sp3. If it is sp3 hybridized, then it is supposed to have what? It is supposed to have tetrahedral geometry. Now, that's true if you don't have lone pair. Therefore, this CH4 molecule has tetrahedral geometry. Please don't forget. Now, even though it's hybridized, the hybridization of ammonia is sp3, but a lone pair is present, and because of the presence of this lone pair, it has deviated from its expected geometry. That expected geometry was what? Tetrahedral. Now, because of the presence of the lone pair, its geometry is what? Pyramidal. Similarly, in case of water molecule, it was supposed to have the sp3. According to its hybridization, it was supposed to have tetrahedral geometry, but because of the presence of these two lone pairs, it has deviated from its what? Its expected geometry, and its shape is now V-shaped or bent, and the bond angle. You can have a look at the bond angles, and this is very important. So, this is the application of VSEPR theory. There are certain examples, more examples, which you have to go through it by yourself. Okay, you have to do it. This part is very important. The questions will be asked from this part as well as from hybridization. No doubt about that. Hybridization and VSEPR theory. So please learn this properly, and if you have any doubts, you are always free to ask me anytime. So with this we come to end of today's class. We'll be seeing you in the next video. Till then, take care. Thank you.